आता म्हणजे ते just wait a minute. Some people they came, classmates came. होते ना? Some discussion is going on offline. Okay, good afternoon to one and all. So in the previous class, we had discussed about the harmonic sources from the commercial loads. That is, we have discussed about single phase power supplies and using the fluorescent ballast and all the things. Okay, fluorescent lighting, and last one that is called adjustable speed drives. We have considered that commercial purpose. Okay. So is it audible? Anyone?
Yes, sir. Yes, sir.
Okay. So today we are going to discuss about same like in commercial loads only. Some industrial loads are there in industry, manufacturing plants and developing plants and all the things over there. So here also some harmonics are going to produce over there. So the harmonic sources for the from industrial loads over there. So industrial side, what we are going to use? Maximum we are going to use converters only we are going to use in the industries. AC, DC conversion, different frequencies of the AC we are going to use and all the things. So many converters we are going to use. Because of that, the converter is nothing but that is static devices we are going to use. Static devices means there is no rotating part at all. That one. So that is a bridge rectifier circuits we are going to use. Bridge inverter circuits we are going to use. So based on that, those all are non-linear loads we are going to call that one. Those all are non-linear loads. Because of that, the harmonics will produce us, and because of that, the power factor will be reduces over there. So again, that is a problem because of harmonics, power factors, and all the things. It is going to down, and to correct the harmonics, we are going to use the capacitors. We are going to use again. So we are for the power factor correction, we are going to use the capacitors again. We are connecting to the lower side over there. Okay, so almost the voltage, whatever the distortions is there, distortion is nothing but actual supply plus the harmonics that will affect only on the low voltage side. Where we are going to connect the capacitor banks at the load side. Load side means we are going to get low voltage only. At the generation side or whatever the transmission side we are going to connect means the transmission side it may be 220 kV, 400 kV and all the things. But where the load side that we have received, we are going to receive very low voltage. So on that side only we are going to connect a capacitor. We are going to connect. So almost the low voltage side only the voltage distortion will affect or it is going to experience over there. Still some people join. Okay, so there are mainly three categories of non-linear industrial loads are there. One is three-phase converters. We are going to call that one. Just now I have told that it may be rectifier, inverters, and all the things. Three-phase power converters we are going to call. Arcing devices or furnaces we are going to call that one. So we are going to do the weldings. We are going to do the soldering, aux, and all the things we are going to produce. So arcing. And saturable devices means which are going to operate at the saturation point. I think in the diode rectification or SCR characteristics, we have considered three reasons we are going to consider: saturation region, cutoff region, active region. Yes or no? MOSFET, IGBT. While doing the characteristics of semiconducting characteristics, where there are three regions will come: saturation region, cutoff region, active region. So which devices they are going to operate under saturation region? So those are saturable devices. We are going to call that one here now. So like because of mainly three reasons only, the industrial loads producing the harmonics here, or these are the sources of harmonics, and these are the industrial load connections here. So read this one. In modern industries, whatever the industries, manufacturing plants and industry areas are there in modern industries, non-linear loads are unavoidable today here. We cannot avoid that one. We have to use, but we have to reduce that one. That is the point we have to understand here. Now those are whatever the non-linear loads are there, that is unavoidable. We cannot avoid that one. We cannot go for the mechanical choppers, circuits, and all the things. We are using the static devices. So by using a mechanical means, again closing the switch, opening the switch, and all the things. So many switching surges will produce heat will be increases. Again, it is a problem. But by using these non-linear loads, the devices, that is static devices, that is unavoidable. We cannot avoid that one. They are injecting harmonics into the system here. That is unavoidable means obviously we are using. So they are going to inject those devices. They are going to inject a harmonics into the system. They are going to use. So these non-linear loads are operating at lower power factor. So whatever the non-linear loads are there, they are operating for the low power factor. Therefore, power factor correction strategies are applied here. We are going to apply power factor correction strategies. What are the power factor correction strategies? Again, we have to use the capacitor banks. We have to use over there. So power factor correction strategies are applied to the system. Yes. Someone had made the voice. Rule number 19, are you there? 19.
Yes, sir.
How many times you will join and you are joining by using different names and all the things. It should not be repeat. Okay. So start that one. So widely using power factor correction capacitors, that is going to magnify the harmonics over. So by using capacitors, capacitor banks and all the things, they are going to magnify the harmonics over there. And high voltage distortions are experienced at low voltage side. So at low voltage side, high voltage, whatever the distortions are there, the previous class at the starting, that is distorted waveforms we are going to consider like this, and all the things. Okay. So like this distorted voltage, it is going to experience at the lower voltage side, that is called capacitor side, where we are connecting a capacitor. So at resonance condition here now. So resonance condition means there are series resonance, parallel resonance. In the series circuit, if XL equal to XC, that is called series resonance we are going to call. If in the parallel circuit, that is XL equal to XC, that is called parallel resonance here. Now based on the circuit connection, if the inductive reactance is equal to the capacitive reactance, then that one we are going to call as the resonance. We are going to call that one. Just a minute. So at resonance condition, that is resonance is nothing but if inductive reactance is equal to the capacitive reactance, that is the resonance we are going to call that one. By considering this one, XL equal to what? Anyone can you tell that one? XL equal to rule number 19. Dipali Medkar.
Yes, sir.
XL equal to what?
2 pi FL.
2 pi FL. Okay. Banase Sagar. Sagar Banase, rule number 30. 32. Dong Ramesh. Dongre Mahesh. If you are not ready to reply for third time, then you will. I will put absent. Mahesh Dongre. Absent. Okay. Rokde, Kiran.
Yes, sir.
What do you mean by XC? XC. Mahesh Dongre. Are you there? So X equal to 1 by 2 phi F naught C, we are going to call that. Okay. Based on this 2 phi, that is the constant value. L is nothing but inductance. C is nothing but capacitance. This F naught is nothing but frequency under resonance. At resonance, F naught is the frequency. So by here multiplying and all the things, we have to find the F naught equation here now. So actually here equation is not there. Just for your understanding, I am telling that. And at resonance is the resonance means this one we are telling here. So at resonance condition, motor and transformer overheating and misoperation of sensitive electronic equipments are occurred. Under the resonance condition, what will happen? The transformer windings are there, or whatever the core material is there, it's going to get heat over there. This increases the heat, motor and all the things. In the motor, again, we are using a core material and winding, both we are going to use over there. So that will produces the overheating over there and misoperation of sensitive electronic equipments over there. Electronic equipments means resistance, capacitors, filters, and all the things. These all are the basic circuit elements. Those equipments, that is active equipments, and those are get occurred over there. So that is going to sensitive misoperation will be leads because of any misoperations over there. Okay, so these industrial loads are mainly categorized into, that is non-linear industrial loads, that is called three-phase power converter. The main load side only we are going to use the converter. Our houses, whatever we are customers, okay, in the industry and all the things, those are the customers, and they are going to use, that is means we are going to use, we are not generating anything, we are use means that is the load side we are going to call that. Some arcing devices where we are going to use welding machines and all the things on that conditions, and saturable devices. These three main places are the sources of the harmonics. One by one we'll discuss this. So three-phase power converters. Converters means we are going to use the bridge rectifiers. We can use, that is 6-pulse bridge rectifier. In the power electronics we have studied about that one. 6 pulses and all the things we have studied. Okay, already we have studied that one. So it may be AC to DC converter, or DC to AC converter, or AC to AC, that is cyclo converter, or DC to DC, that is called choppers. So all converters are there here now. So because of using the load side only, we are going to use there. Those are the electronics, that is the components, that is called non-linear loads. We are going to add that one. So these converters, they are going to produce the harmonics over there. So all the equipments containing static converters. Static converter means there is no rotating part at all in the converters. It is going to convert AC to DC, DC to AC, but the converters are not present over there. So there is no converters at all. All are, that is, sorry, the converters also. There is no static, all are static devices only. There is no movable equipments or, that is, rotating equipments over there. Okay, as variable speed controllers we are going to use, UPS power supply we are going to use, AC to DC converters we are going to use in general. These all are the based on three-phase bridge, also known as 6-pulse bridge, because there is a 6 voltage pulses per cycle, 3 cycles, that is called half we are going to consider, means 6 pulse we have to give that one for the positive half cycle, negative half cycle for each bridge. That is called 3 phase, 1 phase, 1 line. We are going to use that one, 2 pairs. So 6 pulse bridge we are going to consider on the DC output over there. So because of using this 6 pulse bridge, it is going to produce the current harmonics. It is going to produce current harmonics of order 6n plus or minus 1. We are going to call that 6n plus or minus n here, 1 here. It may be plus, it may be 1. We are considering example this n equal to 1. So 6 minus 1, that is called how much it is? 5. That is called fifth harmonics we are going to consider. This integer multiplication, suppose it is maybe 2, we are going to consider. So 6 into 12, 2, that is called 2. 2 minus 1, that is called L1. L1th harmonics we can call that. Like that, this plus or minus we are going to use. If it is 1, that is called 7th harmonic. If it is plus 1 into 2, that is called 13th harmonics. Like that, the odd harmonics which are danger, which will affect, which will misbehave with the power system over there. So because of that, this bridge produces in supply network current harmonics. It is going to produce of order 6n plus or minus 1, which means 1 or more and 1 less than each multiple of 6 over there. It may be n, maybe 1, 2, 3. It may be whatever it is, 1, 2, 3 plus or minus. We are going to do that. In this theory, 6n plus or minus 1, the magnitude of each harmonic should be equal to the reciprocal of the harmonic number. Whatever the harmonic number is there, that reciprocal should be equal to the harmonic of the magnitude. So there would be 20% of the fifth harmonic. Suppose I told that one it is 1, 6 minus 1, that is called 5. So that leaves 20% of the fifth harmonic, and 6 into 2 minus 1, that is called L1, and 9% of the L1th harmonic. Just in the theory we are considering that. So we are taking one diagram here now. By seeing this diagram, you can just see here some noises are there here now. See noises here. Suddenly it is increasing, that one unwanted signals are there. This is the distorted current signals are there here now. See, it is distorted now. It is not a sinusoidal wave here. It is distorted here. So much frequency is changed over there and all that. Same thing they are told. Figure shows waveform of thyristor bridge current against the phase voltage here. No? So commutation notches are clearly visible in the voltage waveform. The source of high frequency distortion components here. These are the notches are there here. No, notches are clearly visible. That is frequency variation, that is called. We are going to call that. So based on this voltage, the current, distorted current is there here. Now see, suddenly one step it is here. Next it will step. Next it will step. That is third one here now. Fourth, fifth harmonic we can call that one. For the continuous positive negative, we can consider that is L1th harmonic, because this one only we are going to consider. Like that, these harmonics will, current harmonics we are going to call that. Power, 3-phase power converters, they are going to affect the current here. Next we'll go for the arcing devices here. So the arcing devices, what it is going to do? Suppose we are doing a welding machine event. It is going to produce the arc. Whenever you touch the metal part, suddenly the fire will start and it is going to join, or some liquid it is going to burn over there. How to burn that one? Very high current is required. The current we are passing, very high currents we are going to pass to produce the arc here. That is here, see here. 60 kilo ampere common here. No currents in excess of 60 kilo, 60,000 amperes here. Okay. So the following are the arcing devices. That is, arc furnaces are there, arc welders and discharge type, lightning over there. The fluorescent, sodium vapor, mercury. Fluorescent lamp previously कैसा था? So ये बटन दबाए तो ऑन हो जाता था क्या? Will take some time. Sparking होता था, क्या नहीं है सर? So that is fluorescent, sodium vapor, mercury lamps and all the things. mercury lamps, slowly it is going to jaisa arc will produce us over there, slowly it is going to intense light intensity will be increases over there. So like that there are arcing devices. These three methods are devices are there, you know. So the voltage current characteristics of electric arcs are non-linear. The VI characteristics of these arcing devices, that is non-linear only. So the following arc ignition, the voltage decreases as the arc current increases. Previously the voltage is more only, but when we will increase the current will be increases. On that condition the voltage will start to decreases. So the voltage decreases as the arc current increases here. As the arc current increases, the voltage will be decreases here. Limited only by the impedance of the power system. So I will consider V equal to IZ. I will consider here. I will consider here V equal to IZ. Because of this impedance is mainly we are going to consider. So Z is inversely proportional to I. Yes or no? Z is inversely proportional to the I. Our current is inversely proportional to the impedance. We are going to call that. So what will happen by using the arc system? The impedance will be reduced over there. So if the impedance is reduced, suppose I equal to 1 by Z, impedance will be reduced. Then what will happen in the current? Current will be increases because it is inversely proportional. That is, current is inversely proportional to the impedance. Impedance will decreases means the current will be increases over there. So for that reason only, limited only by the impedance of the power system here. No, it matters the power system of the impedance will also we have to consider that one. So in electric arc furnace applications, whatever the arc furnace applications are there, that one, the lighting impedance is primarily the furnace cable and LEDs with some contribution from the power system and furnace transformer. We have to use the transformer over there to produce the high voltage. We have to connect that one. Then when the impedance will reduces, then current will be increases over there. So that current is in excess mode. That is called the current in excess of 60,000 ampere are common here. For the arc furnace, the current excess more than 60,000 or 60,000 is common. We are going to call that one here. So the electric arc itself is actually best represented as a source of voltage harmonics. So voltage will be decreases and the current will be increases over there. So voltage decreasing is, that is with respect, that is current will be harmonics are, that is called voltage harmonics. We are going to consider here. On the magnitude, that is harmonic magnitudes are largely the function of the length of arc here. So the arc itself is actually best represented as a source of voltage harmonics. Its magnitude is largely a function of length of the arc. How much length the arc is going to produce, its function is depends on the voltage harmonics we are going to call. So the arcing loads, whatever the arc furnace we are using here now, so arcing load thus appears to be relatively stable harmonic current source. Relatively, the current harmonic sources are stable over there, which is adequate for most analysis. It is required. The exception occurs when the system is near resonance here. We have to accept that part when under or when are near to the resonance condition, when the XL will go near to the XC or XC will go near to the XC. So near to the resonance, the Thevenin equivalent model using the arc voltage waveform gives more realistic answers over there. We are going to use the, for the arc to produce the arc Thevenin's model, we can use that one. So the three-phase arcing devices can be arranged here now to cancel the triple harmonics. The triple harmonics it is going to produce here now. So by using the three-phase arcing devices, we can arrange it. We can cancel these harmonics here. Okay. However, this cancellation may not work here now in three-phase arc furnace because of the frequent unbalanced operation during the meeting in phase. So three phases means all three phases should be balanced condition. So because of the unbalanced condition, this cancellation will also, it is not applicable, we are going to call that. So the cancellation may not work in three-phase arc system. So during the refining stage, we are going to refine that one. When the arc is more constant, arc we are going to, it is not a fluctuation and all the things, it is more constant. So the cancellation is better on that condition. If arc is constant, then we can, the cancellation is better way we are going to consider here. So this is the arc devices here now. How, which triplen means is nothing but third harmonics we are going to produce. It is going to produce during the arcing furnace, lightning, or arc welders and all the things here. The last one that is called saturable devices here. The saturable devices we are going to consider, the saturation part it is going to consider actually the core material we are going to use in the motor and transformers and all those. So the steel cores we are going to use that one. So because of that one, the saturable, the harmonics will produce us. The yesterday class also we were discussed about that. Means the energization of the transformer, suddenly the high interest current will flow and all the things. Okay. So the saturable devices in this equipments in this category includes the transformer and other electromagnetic devices here. So the equipments include here is nothing but transformers will come. So the transformer has main, suppose any you can consider three single phase or three phase. It has core and winding, quite both. So the magnetic core we should have to use over there. So the core material that may be steel material we can use over there. That is the called electromagnetic devices. With a steel core we are going to use that one. Steel core we are going to use, including motors. We can use including motors also we can use here. So harmonics are generated, the harmonics will generate due to non-linear magnetizing characteristics of steel. Because of the non-linear characteristics of steel, the harmonics will produce us here now. So power transformers are designed to operate below the knee point of the magnetic saturation characteristics. So whatever the knee voltage is there, knee point we are going to call. If it is below that one, it will not go up that one. So once the knee voltage is more than knee voltage, it will not come down. So like that, that knee point is there. So based on that, the power transformers we are designed to operate below the knee of the magnetic saturation characteristics. The selection of the operating points depends on, we can select the operating point, how we have to select this knee point here now. The cost of the steel, load losses kya hai, how much noise it is going to produce, how efficient it is, and all the things we are going to consider, and some other factors they have mentioned here. Efficiency, steel cost, no load losses, noise, these are all the things we are going to consider here now for the selection of this knee point here. Some transformers are purposefully operated in the saturated region. So as per the requirement, we application orientation operation we want that one actually. The transformer, some people they are going to use for the protection of their devices. Some people to reduce the voltage they are going to use. To increase step up for the high current they are going to use here now. As per the requirement of their our application oriented design it has, and we have to use, we can use the transformers over there. So what they are telling here now, some manufacturers are purposefully operated. Just a minute, battery low hai. Purposefully operated in the saturation region we are going to operate here. One example is that is a triplen transformer used to generate 180 hertz for the induction furnaces here. Induction furnaces 180 hertz we are going to use. So motor also exhibits some distortion in the current when overexcited. After overexciting the motors, winding and all the things. So these motors, by using here, including motors only we have considered, those motors, what they are going to, they also contribute or they are going to exhibit some distortion in the current here now. Although it is generally of a little some consequences we are going to call that. There is no, that is much more consequences, only little consequences are there. There are, however, some fractional horsepower. 1 HP motor, 2 HP motor, we are going to use that is. So fractional horsepower can consider. So single phase motors that have nearly triangular waveform with significant third harmonic currents, we are going to use that one. So see here, this is some current waveforms that is very high harmonics, third harmonics they have here now. See, this is the harmonics actually. If the magnitude of the harmonics is more, that is it will not, it will affect more here now. This is the harmonics here now, positive side, negative side, and all of these. So the waveforms for single phase star connected, star grounded three phase transformer here now. This is the grounded three phase transformer current waveforms here now. The current obviously contains a large amount of third harmonics here now. It contains the large amount of third harmonics. By using, suppose here it is a star connected, that is Y, that is called Y, we are going to call that one. So in the delta and Y, they have to like this. This is Y, we are going to call that one. So this one is a star connected, we are going to call that one. So the delta connection and ungrounded here now. Here the star connection we are using and grounded we are using here. We understood that by seeing this waveform, this will produce us very high harmonics, large amount of third harmonics they are going to produce here. So delta connections and ungrounded star connections prevent the flow of zero sequence harmonics here. It is flowing to zero sequence only here. It's crossing to the zero here now. Flow of zero sequence harmonics, which triplet tended to be the line current will be wide these harmonics unless there is a imbalance in the system here. So there is, if the large amount of the third harmonics are there, then what will happen? It is going to wide the harmonics or current will be wide over there. So these will imbalance the system, whatever the R, Y, B, three phases are there. So one phase, the current will be very high. So if the current will be very high, the power or load will be increases over there. So because of that increased load, what will happen? It will unbalance or imbalance will be occurs over there. There is an imbalance in the system. It is going to occur over there. So we have to consider, we can use instead of this star connection or grounded star connection, we can use delta connection, and we can use the ungrounded star connection system. We can use that one to reduce that harmonics here. So these are the sources: arcing devices, three phase power converters, and third one is saturable devices. These devices where we are going to connect, we are going to, those are the sources for the harmonics, and these devices we are going to use in the industrial application. For that reason, these are industrial loads, we are going to call that. So locating harmonic sources here, we understood that because of this power converter, because of using the fluorescent lamp, because of building the arc furnaces, okay, by automatic speed control, we understood that the harmonics will produce here. How to identify location of that one? That is called locating harmonic sources. We have to locate that one here. Normally the harmonics will flow towards the sources, but if we have connected a capacitor we have connected means that is also, it will act as a source only. So all the harmonics shift towards the capacitors. So first we have to remove the capacitors, then we have to connect it, and then we have to observe the voltage across this one, and we have to consider, we have to check that one high currents are there or not, and it is a under resonance, it is there or not. We have to check that all the things here. So by checking this and doing the measurement, we can say that we can, the location of the harmonic sources, we can identify that. And radial utility distribution feeders, we are going to consider the feeders, industrial plant power systems. The main tendency is for harmonic currents to flow from the harmonic producing load to the power system source. From the load to the power system source the harmonics will be produced, flow over there. So the impedance of the power system is normally the lowest impedance seen by the harmonic current here. If the harmonics are more, the current on that condition, normally that is lowest impedance we were having here. We have previously also we have discussed that one. Thus, bulk of current flows into the source. Very high current will flow to the towards the source, towards the generation side or transmission side. We can consider where we are going to get that one. Source we are going to call that one. This general tendency of harmonic current flow can be used to locate the sources of harmonics. To locate the sources of harmonics, we are going to produce the harmonics and we are going to identify where they are going here now, from where is that. So to locate that one, we have to use the power quality monitor capable of reporting the harmonic content on the current here. So the harmonic current content, we should have to monitor that current over there. In the power quality system, we have to monitor the current here. So the monitoring system we have to use here now, using a power quality monitoring here now. So that is capable of reporting the harmonic content of current here now. It should have to report the content of harmonic current. Okay. Simply measure the harmonic currents in each branch here now, starting at the beginning of the circuit and trace the harmonic to the source over there. Starting at the beginning of the source or whatever the supply we are going to use, we have to observe that one, whatever the current values there. So and after that, after some resonance and all the things, adding capacitors or removing that one by rearranging the system or circuit, you can again we have to measure here. Now, the power factor correction capacitors can alter this flow pattern for at least one of the harmonics here. We have to alter this by adding a power factor correction capacitors. So it is going to alter at least one of the harmonics. It is going to alter that one here. So adding a capacitor to the circuit, we are going to add a capacitor into the circuit, may draw large amount of harmonic. It is going to draw over there harmonic current into that portion of the circuit where we are going to connect a capacitor. In that place, that is going to draw the large amount of current. It is going to draw over there. In such situation, following path of the harmonic current will lead to a capacitor bank instead of the actual source here. Now, instead of actual source where the harmonics will be produced, so it will flow through the towards the capacitor. We are going to call that one. I will show one diagram here now. Just a minute. See here. Here the feeders are there, loads we are connecting here now. So they are going towards the sources here now, towards general flow of harmonic current in the radial system we are going to consider here now. The radial system, whatever the dotted line is there, these are going towards the sources here. But when I will connect the capacitor here, see here, I have connected one capacitor. Here I have connected one capacitor here. So all that is the path, it is altered. Normal path was this one. But when the capacitor is connected here, now the path is altered and the capacitor is going to draw the capacitor or whatever that harmonic current it is going to draw over there. So this is the location we can consider that one. The power factor capacitor can alter the direction of flow of one of the harmonic component here. Now here harmonic component is there, here are harmonic components. If I have connected a capacitor, it is one harmonic path, it is changed. And here we have connected means it is going to change over there. It is going to change over there here. In general, it is necessary to temporarily disconnect all capacitor to reliably locate the sources of harmonics. Starting, we have to disconnect all the capacitors. Then we have to connect that one. Actually, it is usually straightforward to differential harmonic currents due to actual sources from harmonic current that are strictly due to resonance involving a capacitor bank. So at the resonance, that is called, because the harmonic current it is going to flow due to the resonance here only, it is going to involve at a capacitor bank over there. So a resonance current typically has only one dominant harmonic riding on top of the fundamental sine wave. On top of the fundamental sine wave, so there is only one harmonic, it is going to visible or it's equal to riding over there. So none of the harmonic sources presented earlier in this chapter cover mein, leave that one. They all produce more than one single harmonic frequency. Here two harmonics we have considered just for understanding here now. So one harmonics we have can divert that path, already have shown. See the waveform. Waveforms of these harmonic sources have somewhat arbitrary wave shapes depending on the distorting phenomena, but they contain several harmonics. This is the normal path here from the load. Here it is going to source is transferring over there. So somewhere they have mentioned that one. Okay, it contains very large amount of. The fact can be exploited determine if if the harmonic resonance is the problem, then are likely to exist in the system with capacitor. Okay, with capacitor we are the resonance will be existing over there. How to identify that one? Okay, simply problems are likely to exhibit in a system with capacitor. Simply measure the current in the capacitors. What we have to do, we have to measure the current in this capacitor. We have to measure. If it contains very large amount of current, it is constant, then we can say that one it is the harmonic is it is going to draw some harmonic current. Already it has drawn some harmonic current. We have to consider that one here. So can locating the harmonics, we can call that one. If it is going to one harmonic, it is going to divert here. So we can measure the current flow, current across the capacitor. That if the current is very large, then we can consider that is the harmonic or resonant current is there here. It contains a very large amount of one harmonic other than the fundamental here. Other than fundamental, it is likely that the capacitor is participating in a resonance circuit within the power system here. If the fundamental current is there, whatever the rating of the capacitor bank, based on that the current is fundamental. How much current is flowing here? No, same current is there. Then if it is more than that, it is greater than or very large current is there, we can understand that it has drawn some harmonic currents. Also the resonance occurred over there, we can call that one. So always we have to check the capacitor current first in any installations where harmonic problems are suspected here. Now suppose in a system we have to connect anywhere, we are going to connect any systems and all the things, we have to check the current first, the harmonics are present or not. So if the without harmonics are present, then also you have connected means the resonance may occur over there, because it is going to draw, the capacitor is going to draw the higher current, that harmonics current it is going to draw, and that is going to the resonance will occur over there. So like this normal the location, it is going to go towards the source, it is going to do whatever the harmonic currents are there, they are going to flow towards the source over there. So we can easily locate those sources or locate the harmonics here. So we'll stop here only. The next we'll discuss about response for these many harmonics, how the power system it is going to respond, what are its characteristics, what is changes in the impedance, series resonance, parallel resonance. These are all the things we are going to discuss in the next class. We'll discuss that one. Just a minute, I will attendance, I will mark directly. I will check who all are present and I will mark that one. I will not call your roll number. Okay, we'll stop here only and we'll continue in the next.
सर
बोलो,
नोट्स ओपन नहीं होते आपके?
चेक करो ना, आप ऐसे कैसे बोल रहे हैं? अभी चेक करो.
नहीं, एक्सेस रिक्वेस्ट पे भेजे फिर
कभी चेक किया मैडम? कब चेक किया आप?
कल.
हाँ, अभी चेक करो, चेक करके मेरे को वापस मैसेज करो क्या है वो.
ओके सर.
चेक करो आप, चेक करके बाद में इश्यू लेने का. ऑलरेडी yesterday only I have done that one. I have given access to all of you peoples.